what we were doing last time. So let me summarize what we did on Friday. On Friday, we started exploring a particular conformal field theory called n equals 4 super Yang-Mills. Here is the Lagrangian. I could have started giving you the Lagrangian in 4 dimensions right away. Then this is the kind of things I would write. I would write that it looks like pure glue, trace of f squared, and then there is some kinetic term for some scalars and some quartic scalar interaction, and there are a bunch of fermions. And we could have started with this 4-dimensional action, forgetting that the most natural way to think about this is as a reduction from 10 dimensions to 4 dimensions. Then we started asking, what's the simplest possible question we can ask in this theory that has no scale? If a theory has no scale, 2-point correlation functions, they can only depend on the distance between the two operators through a power law. So the simplest set of observables in a conformal field theory are the set of critical exponents, the set of dimensions, which are this capital delta I, associated to each local operator in my conformal field theory. And what we saw is that if there are many operators with the same classical dimension, if you have many operators with the same classical dimension, for example, if you have all these operators, O capital A, where A stands for the collection of these indices, I1 up to IL, where each I runs from 1 to 6, so there are 6 to the L such operators, right? All of them have dimension L. There is a huge degeneracy. And we have to lift this degeneracy. And how do we lift this degeneracy? By considering the good operators of the theory. What are the good operators? They are a linear combination of these bare operators with some coefficients psi that we can call wave functions. And these coefficients are fixed in such a way that this operator diagonalizes the so-called mixing matrix, gamma AB, that we find when renormalizing the theory by looking at the coefficient of logarithm of the cutoff in the bare 2-point function. And the claim is that if we construct this combination and then multiplicatively renormalize it by cutoff to the power of the anomalous dimension that we get, which is the eigenvalues, which is related to the eigenvalue of gamma, then these operators have definite anomalous dimension, which is just a classical dimension plus the eigenvalue of gamma, and this therefore gives you the spectrum of the theory. So to compute the spectrum of the theory, we need to compute this matrix gamma, and we did it up to a constant that now I'm telling you that is equal to 2, but up to a constant, we found that it was equal to a constant times the trace operator minus twice times the permutation operator plus some constant times the identity. Okay? Is it clear so far? Okay. Now let's make a few comments. Again, let's summarize. So gamma is a spin chain, can be thought of as a spin chain Hamiltonian. Okay? So let's emphasize here that this, of course, is trivial. This is just notation. This is just a statement that if you don't like the notation that we use for OA, you can trade it, you can put a cat symbol if you like. This has the same information as that trace there. It is just a map. There are 6 to the L's object on the right, 6 to the L on the left, and if I have some matrix that mixes OAs amongst themselves, that acts on OAs to give me another OA prime, I can translate it into a matrix that acts on this cat and gives a cat-cat prime. So that's trivial. The Hamiltonian that we got is local. That's also trivial. This just follows from large n, right? Because at large n, we saw that the interactions, these ones are much bigger than the interactions where this line would have to pass by and interact with someone far away, because those you could not draw on a plane. So just by large n, you have to start with interactions which are nearest neighbors before going to next to nearest neighbors and so on and so forth. So the fact that it's a local Hamiltonian is also kind of straightforward. The Hamiltonian has SO6 symmetry. It is constructed out of SO6 invariant tensors, which is also trivial, because the Lagrangian has SO6 symmetry. Right? The Lagrangian, which came from compactifying from 10 to 6 dimensions, this index I runs from 1 to 6, and I can rotate these scalars among themselves. Right? There is a symmetry that rotates this vector phi by any rotation times the vector phi, all the fields. You can just rotate the scalars amongst themselves, and it's a symmetry. So, of course, whatever I will get should respect this symmetry. Now, what is very non-trivial is this last part. This is what is really non-trivial. Which is that the Hamiltonian is integrable. We saw, when we started studying SO6 Hamiltonians, that there are many SO6 Hamiltonians. By symmetry, all of them are given by a combination of these three tensors. But what is very special is this relative coefficient between these two guys. This relative coefficient is -2 for an integrable chain. You remember, so if it follows from this R matrix construction, we fix the R matrix and so on. And therefore, this is kind of a very nice surprise. It's like a Christmas gift. Right? We could have asked for all of this, but we did not have the right to ask for such nice integrable spin chains. And we got this gift. So somehow there was a Christmas gift. Someone said, okay, you behaved properly. Okay, here is an integrable spin chain. Now, who is giving us this gift? Where is this gift coming from? And the answer is string theory. Right? So this gift that we are getting, this integrable gift, is coming secretly or directly from string theory. So let me argue a little bit why this is indeed what is going on. So first, let's see. Why do we get this -2? Why -2? -2 has a trivial explanation. -2, remember, was directly related to just having a commutator square as an interaction. It was the commutator square when we did a combinatorics that it is phi I, phi I, phi j, phi j, minus phi I, phi j, phi I, phi j, and the combinatorics of this interaction vertex was what gave this -2. But where is this interaction vertex coming from? How do we get such interaction vertices which are commutator squares? We get them if we do compactifications. Because we start with f square in some higher dimensions, we compactify, and the dimensions that we are not using will give this commutator square. Right? Remember, this was just coming from f mn square. So this is kind of an effect of compactifying. Okay? But it's more than that, because by itself, the -2 is not important. Remember that this coefficient was -2 for SO6, not for SON. For SON, it was a function depending on n -2. Okay? This -2 is good for SO6. But what is this 6 here? This 6 is just 10 minus 4. It is just a statement that we start not in a random dimension and we compactify, but we start in string theory's favorite dimension. We start in 10 critical dimensions, and we went down up to 4 dimensions, which is where gauge theories have the potential of being conformal by dimensional analysis. So we compactified to 4 dimensions, which is the dimension where we could have a dimensionless coupling, where the gauge theory could be conformal. And because we start with 10 dimensions, which is string theory's favorite dimension, the residual symmetry that we get is SO6. So this 6 is a compactification. All these things is because it comes not from a random compactification, but from a compactification from 10 dimensions. So it's clearly hinting that if we want to understand better the origin of what's going on and really why we are getting these nice Christmas gifts, probably we should go and look at what string theory is telling us about this theory in looking for an explanation for what is, at this point, kind of a remarkable coincidence. That out of all Hamiltonians we got something that because of the very 10-dimensional flavor of the theory, as I told you, this is a theory in 4 dimensions, but many things smell like 10 dimensions. We have 6 scalars, which is 10 minus 4. We have gamma matrices of 10 dimensions. All the ingredients in this Lagrangian, even though the theory is a 4-dimensional kosher theory, remind us that its origin is in fact a 10-dimensional origin. Okay? So we will see that indeed, by thinking about string theory, we do get new insights about what could be the origin of this mysterious integrability. Yes? Yes.
Is there anything we can say about, is there any reason why we should expect nature to be integrable?
No. No. Now we have to ask, why did we get this gift? Yeah. A priori, we did not have any right to expect this to be integrable. This is what I'm trying to emphasize here. Trivial, 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 very non-trivial. Very good. Now, there are two things you can now do. Instead of considering these operators, consider even more general operators, or even simpler operators. Okay? So if we start with this OA, we could go to OA, and we could go to any single trace operator, trace of anything. It could contain psi's, it could contain covariant derivatives of phi, it could be more general than what we wrote. What would this give? Well, again, it would give a spin chain. Again, it would give us local spin chain. It would give a spin chain with a bigger symmetry. We would have to understand what is the symmetry of n equals 4 super Young-Mills. SO6 is a subgroup. In general, it's a bigger symmetry because the theory is supersymmetric. There is a symmetry that rotates fermions into bosons and so on. So it's a bigger symmetry. And this will lead to a bigger symmetry group, a spin chain with a bigger group. I'm not going to give many details, but this is going to give a more general spin chain. And once again, very non-trivially, if we were to do this computation, it's again, we will find that it's again integrable at one loop when we are doing this one loop computation. Okay? We could also go from one loop to higher loops. I don't want to comment on this at this moment. I want to comment at this after tomorrow, or tomorrow. But we could do this and ask, do we still find integrability as we go to higher loops? Let's postpone this, but it's a very good question. And finally, I could simplify and could construct two scalars, z, which would be phi1 plus I phi2, and x, which would be phi3 plus I phi4. Okay? And the claim is that we can construct operators made out of just these guys, z's or x's. So let's see that if we start with this and act with the Hamiltonian, we stay within this family of operators. Okay? So if we act with identity, we stay within the family. If we act with permutations, we permute a z and an x, but we stay within operators made out of just z's and x's. So what we have to be careful is what happens when we act with a trace. So let's check what happens when we act with a trace. So clearly, trace acting on zx is equal to 0. That's trivial because they don't have common fields. Remember, and trace, right? You remember that trace acting on phi a, phi b gives delta AB times sum from C equal 1 up to C of 6. So if they don't have any field in common inside Z and X, of course the trace gives 0. But what about trace acting on ZZ? Well, this gives trace acting on phi1, that is non-zero. But then because of that I there, we get minus trace acting on phi2. The off-diagonal terms is 0 because they are different. And because of that, this is also 0. So if we start with these operators, if we construct these complex combinations, automatically only identity and permutation matters. So it means that the Hamiltonian, when restricted to just z or x, becomes lambda over 16 pi square identity minus permutation acting on sites n and n plus 1. But this is nothing but the Heisenberg Hamiltonian that we have been spending so much time with in the first few lectures. So in this case, the map to spin chains is even nicer. The way we think about this guy is we say that a z is a spin up and an x is a spin down. And then we even are in the domain of the usual spin chains that people consider. It's not even an SO6 fancy spin chain. It's really the usual SU2 spin chain. Okay, so what we did was identify an SU2 inside an SO6 and saw that the corresponding spin chain is an SU2 spin chain. Okay, so there is an SU2 subsector inside, which just is Heisenberg spin chain. So everything we have done about the Heisenberg spin chain would have implications, and you could translate back to statements about the spectrum of a particular class of operators in n equals 4 super Young Mills. All these bit equations that we were seeing, they are, if you solve them, you are now knowing information about the correlation functions of operators in this 4-dimensional gauge theory. Okay? So everything we said now as another new use, another use that we were not expecting, which has nothing to do with condensed matter, but rather with high energy and with understanding the spectrum of this n equals 4 super Young Mills for this particular class of operators. I could have started my discussion, instead of considering that class of operators, considering just this class of operators with z and x. But then, suppose I had started our discussion directly from the beginning with just z's and x's. It's a smaller class of operators. What would I get? A spin chain Hamiltonian, that's trivial, which is local, that's trivial, which has SU2 symmetry, that's trivial, and which is integrable, but in that case it would also be trivial, because there will be only one tensor I could construct, which will be the permutation, right? So it's not really a very good check. I mean, then it's not a present, it's a triviality. There's only one Hamiltonian with SU2 symmetry, as we saw, so it has to be integrable. It becomes, you need to consider something a bit more general, a bit non-trivial, and that's why SO6 is such a good example. Okay. There was a question. Yes. No, it is just one SU2 inside SO6. Choosing other operators is just looking for other SU2 subgroups inside SO6. Other questions? Yes?
The analogy between correlation functions in n equals 4 super Young Mills and spin chains seem to work for the 2-point functions. But Young Mills also has like higher correlation.
Very good. Yeah, that's an excellent question. So in a conformal field theory, the starting point, the simplest question we can ask is 2-point correlation functions. Once we solve 2-point correlation functions, we can ask what about 3-point correlation functions? And then once we solve 3-point correlation functions, we can ask what about 4-point correlation functions. And you see the pattern. Now, there's a couple of nice things to say. One is that because the theory is conformal, in fact, it truncates there. Once you know 2- and 3-point functions, it's actually possible to reconstruct all higher point functions. Because in a conformal field theory, there is a statement that if you know all 2- and 3-point functions, you can reconstruct all higher point correlation functions. So if you were in the CFT course, you know this. If not, it's just a statement. You can trust me. I can tell you why it is. But yes, we have 2-point functions is not a full solution of the theory. Then we have to go and study 3-point functions. That's a more advanced topic. We did not even finish solving 2-point functions. We are starting to study 2-point functions at one loop. There are 2 loops, 3 loops, 4 loops, 5 loops, strong coupling. There is a lot to do, even concerning the simplest observable. But it's an excellent question, once we will solve it, if we are able to ask, can we now go and really nail down the theory and go to 3-point functions? So that will be amongst the advanced topics I will try to start discussing in the last lecture. Any other question? Yes.
So the original correspondence was you have a spin chain Hamiltonian which solution, the eigenvalue will correspond to some normless dimension or
yeah.
So now if you restrict yourself to this kind of X and Z field, then
yeah.
the string side, the loop calculation, actually you only involve this field that is within this subgroup.
That's right. We showed that permutation identity stays within this group, and trace kills operators of this form, right? And therefore, when you act with Hamiltonian, you stay within this family of operators. So it's fine to diagonalize, restricting yourself to this set of operators.
So wouldn't that the loop calculation is only part of the whole loop correction? Because you only calculate the loop correction from some specific field.
No, the Hamiltonian is a big matrix. Then you can ask whether it's reducible or irreducible. You can ask whether if I have this big matrix, are there subspaces that if I act on these subspaces, I stay within these subspaces? And the answer is yes. In fact, you can just, what we are doing here, you see, by taking a scalar and constructing a complex scalar is giving charge to this scalar. So now this scalar z has a 1 unit of u1 charge, where the u1 is the symmetry that rotates phi1 and phi2. So what's happening is that we are restricting ourselves to fields that have some set of quantum numbers and some total classical dimension. And then you can see that these are the only set of fields that have those quantum numbers and nothing could mix with them. Okay? Said differently, what we are doing by considering this combination is giving arrows to our fields. So now we can have an identity, a permutation, sorry, we can have an identity, but we could not have a trace, because if we put incoming fields, this would not be allowed. We cannot annihilate things with charge. So what we are considering is a subsector, where by charging our particles, they can no longer annihilate because they have charge. Okay, good. So this summary took way longer than I want, but that was probably to be expected. So now I will present to you what I think is probably one of the most important arguments in theoretical physics over the last 20 years, which is the decoupling argument of Juan Maldacena, which led to ADS-CFT. Okay? So now we go, and I'll tell you about what's called the decoupling argument. Okay? So what I will tell you is about a sketch of a derivation of ADS-CFT, which has to be a sketch because ADS-CFT is a conjecture. But it's true. Okay. So I'm going to be sketchy. I'm going to tell you. So the basic idea, so there are a couple of ideas. Let me first tell you what's the spirit of this derivation. What are the kind of key ideas that are involved? One key idea that is involved is the notion of open-closed duality in string theory. So I know Davide told you a little bit about it, but let me just remind you what this is. This is just a statement that, for example, the simplest example we can see of this duality is if we imagine that we have two branes, which are these two planes, and we have this picture here. Okay? Now, what do you see when you look at this picture? Some people will say it's a closed string emitted by this brane. So this brane pops a closed string, and the other brane absorbs the closed string. So this can be a closed string emitted by the left and absorbed by the right. It's indeed a totally legitimate description. Branes, you can think they are sources for closed strings, and they emit closed strings. Okay? That's fine. But we can think in a different point of view. We can think the picture like this, where we evolve time like this and not like this. And then we say that this looks more like an open string that I stretch between a pair of branes. I stretch an open string. And I consider its time evolution in periodic time. So I compute some open string partition function. Okay? So in string theory, there's often this notion that you start drawing pictures, and you should not be too attached to a particular description. You should not insist, oh, this is closed strings for sure, or this is open strings. Sometimes you can draw the same picture, and different people can arrive at the blackboard, start putting time in a different way, and some people see closed strings, and some people see open strings, and both can be totally right. And at the essence of ADS-CFT, of this duality that we will see between CFTs and gauge theory, we can think that at the essence of this duality is precisely this open string duality. The fact that different systems, the same system can be described by two things that might look different, but in the end we know are exactly the description of the same thing. Okay? So again, this is inspiration number one. Okay, so this is inspiration number one. Inspiration number two, which is related to this kind of idea. Number one, I like to consider another example, which is, suppose we want to consider an example where we have an heavy proton and here, passing by the heavy proton, we have a light electron. And we want to study how a light electron passes by a heavy proton. So what happens? Well, first approximation, they throw a photon at each other. But then there are other effects that you need to start taking into account. There is the so-called Bremsstrahlung effect, where you have some emission. And there is vertex corrections. And there are self-energy corrections. And so on and so forth. And all in all, this vacuum polarization, vertex correction, Bremsstrahlung effect, and Coulomb interaction, all of them together, their net effect that is telling us how the electron is deflected. So in the end, we can translate this by saying, instead of thinking that there is a proton and there is an electron and there are interactions, forget about the proton and just say that the electron lives in a kind of non-trivial background. And we trade this electron, we trade this by some non-trivial background, that is some non-trivial potential V of R. So we remove the proton and keep its effect, which is its potential that it generates. Which would be what? Which would be the usual Coulomb potential, minus alpha over R. And then you start computing and you get 1 plus alpha over 4 square root of pi, mass of the electron times R to the 3/2 e to the minus mass to the electron times R, some kind of corrections like this, which are corrections. It's called the U-length potential or something like this. And if you were powerful enough, you could compute all corrections to the Coulomb potential due to these quantum effects. And if you were, you would do, again, you could, instead of considering all these Feynman diagrams and so on, you would say, no, the proton, I replace it by a background, by a non-trivial potential, and now my electron moves in this non-trivial background. Okay? So I have either the probe, either the proton, and then I consider all these interactions, nothing plus Coulomb, plus self-energy, plus dot, dot, dot. Okay? And then both the proton and the electron are in flat space. Or I forget about the proton, but then the electron is not moving in empty flat space, it's moving in the presence of a background. Okay? So this is electron in a non-trivial background. Okay, so now let's try to transpose these ideas to something closer to what we are doing. Okay? So the conclusion here is either Feynman diagrams or, but not both at the same time, background.
So,
yes.
When you write down this background term, this is not just a mean field theory, right?
No.
Otherwise, you're not going to get all the. How do you get that?
You just compute all these diagrams, and how do you compute a Coulomb potential?
Right. Okay. So
you compute Coulomb potential, but then you do a better computation by taking loops into account. So now, what we want to do is consider something more realistic. And instead of a proton, we will consider a stack of brains. So the stack of brains means that you put a pile of brains all at the same position. And we will put here capital N brains. Okay, so brains are again the places in string theory where open strings can attach. So by putting n, where n will be big branes, you're putting there some very heavy object. So it's like our heavy proton and our light electron will pass by it. Okay? So now we put there n branes. So this is our heavy object. Okay? And now we will study what happens when strings interact with this heavy object.
Are you specifying what dimension?
Ah, good, good. So we will consider, let's consider D3 branes. So 3 dimensions of space, and they are there for any time. So did someone not take string theory? Who did not take string theory? 4 people. So again, what is a brane? A brane is the following. So you have strings. Strings are loops, right? So they move in space-time and so on. This is the simplest kind of loops, which are closed strings. So you just write an action for some vector in space-time moving around, like we did for Landau-Lifshitz. You see, you had some vector n of sigma and tau that was describing some loop. And this is basically what string theory is. It's a theory describing this loop moving in space-time. But that's what you get if the loops are closed. If the loops are open, you need to specify what happens at the endpoints. And then in string theory, there are branes, which is just you define as hyperplanes, where the endpoints of the string need to end. So they are attached to these hyperplanes. They have to be attached somewhere. We call the positions where they are attached, we call them branes. In particular, we can consider 3-dimensional branes. And then on these 3-dimensional branes, I have my stack of branes. And I can have a string attached to these branes, which is just specifying that the boundary conditions, n when sigma is equal to 0 must be in this plane, n when sigma is equal to 1 must be also in this plane. Otherwise, n fluctuates in space-time. Okay? So, anyway. For the most part, cartoons will be enough, but it's true that some familiarity with string theory will become more and more useful as the course progresses. But it's not totally crucial to know everything about it. So please ask if you have any question. If something is not clear, I will try my best to, but of course it's a bit impossible to cover all string theory in the meantime. So we have these strings, these open strings here. This is an open string. But in fact, whether it's an open string or a closed string, we will soon see that it's the same story as above. It will depend a bit on how we will see this picture. Yes?
So why is it crucial to have n branes stuck on each other? Can't we just put all the strings on one brane? Or?
We will see.
Okay.
We will see what would be the difference in having n branes or one brane. So now, what happens with a string? So let's suppose we have our branes, and we send a closed string, our graviton, when it's flying and approaching the brane. We are sending it, time is going like this. And then what happens is that at some point, this string can touch the brane. As it touches, it can attach to the brane, start propagating like this, propagate. Eventually, it could even do like this, and if this point touches the brane, it could split into 2 strings. And then if each of these 2 strings, for example, could rejoin again, and it could give 2 closed strings that then propagate, and they go their own life to infinity. Okay? So imagine these pieces of rubber going, attaching, splitting, doing whatever they want, and flying back again. Okay? Is it clear? That is, we will draw some pictures. Let me now draw a more vigorous picture. Again, whenever I draw a plane, I mean a stack of branes for reasons that will become clear soon. We can have some picture like this, where in space-time what's happening is that I have one string interacting and coming out, and as it comes about, it could split into 2. It could have some holes, and it could do this. Or it could, I could imagine a string coming. Let me see if I can draw this. Where now here, you see, I would have You see what's happening? The string, it's this picture here where the string splits into two, then these two would join, and then it would go out. You see? This is a string, attaches an open string here that goes from here to the other side, and this open string splits into two open strings. One goes here, the other goes there. Then these open strings join into one, and then they leave.
So, just a sort of question about the conventions for your drawings. By closing those, you mean that, I mean, closing your lines, you're talking about open strings as opposed to world sheets, right?
I didn't understand what you said, sorry.
So when you close your lines in, like in the
Here?
right? That's an open. I mean, all of this. This is just the open string as opposed to the world sheet, or is it the world sheet?
What is the difference between a string and a world sheet? A world sheet is the surface drawn by the string.
Yeah. So on the left-hand side, it's just, I mean,
Here?
yes.
Yeah, here I do snapshots.
Right, exactly.
And here I join them. Like when we draw a space-time diagram on a particle, we put a line instead of putting many dots.
Right. So.
Just the same. So it's the world sheet being swept by the string as it moves in space-time. Okay? And then we could have more general cases where we have this string coming in, splitting into two. Not sure I can draw this properly. I mean, I know I cannot draw this properly. This is not bad. It's a bit terrible. Okay. You see what I mean, right? And then you could have more than one splitting, and then the string could go out. You see what's going on? You have the string, and then it merges, splits, and goes away. It can have holes in the middle of the string. This is at the brain and so on. Yes?
You've got in the first picture where you distributed the individual strings at the slices of time, you've got two strings going off.
Yeah, here I just put one string coming in and one string coming out. I could consider more general case where I put two strings going out. Yeah. Okay, it's a bit tough. But you see what I mean. You have a closed string of loop, it interacts with the floor, and then it becomes out. Okay, now you can draw the space-time picture with better pictures than this for sure if you are better at drawing. Okay? And now the basic idea is quite clear. The basic idea will be to say, well, but then probably I can think of this string that propagates. I forget about the brains and just say that perhaps I can think of this as a string that comes in and goes out in some non-trivial background. That's the goal. The analog of our potential that we resolve. Okay? So in other words, when we think like this, we have open strings that are propagating, and then, for example, here we have an open string propagating. There we have an open string that splits into open strings, that splits in one open string, that goes away. So this is kind of the open string direction. But if we think from this point of view, we think rather that this is emitting closed strings. So this is kind of the closed string picture, where we cut like that and we see that this brain is popping out closed strings. And if you have more than one hole, more than one interaction with the brain, it's like it's emitting several closed strings. And we have a brain, a string propagating and being hit by all these closed strings that the brain is emitting. So the cartoon, of course, for example, thinking about the closed thing, is that when we have something like this being emitted, we can think of this from the worldsheet point of view as saying that I have my worldsheet, and I'm inserting a particular operator, which is called a vertex operator, which you can think that this is kind of a path integral, where I cut some boundary, and that boundary, I could imagine I cut it, now I continue the path integral, and I close the path integral. It's the same when we were drawing this sphere, and we were saying I excise some small circles, and now a sphere becomes a cylinder. I could have excised, become a cylinder, and then complete by the path integral and become a sphere again. So there's often this description, this is nothing but operator state correspondence, if this is familiar to you, where I trade having some boundary by some vertex operator that I would put on my worldsheet. And in that case, when I would be summing over, the picture would be, and this is very cartoonish, and we'll try to go and make it more and more precise as the day goes. As we would sum over all these insertions of these vertex operators, we would sum many of them, they would be all indistinguishable, we would sum with 1 over n factorial and so on. And the claim is that this would give something like an exponential, because they are all indistinguishable and we have this 1 over n factorial, of some integral, of some vertex, of some integrand that will depend on sigma and tau. And you see that because it's in the action, it's kind of a correction to the string action, which we can think of, which modifies the background. So we modify our string Lagrangian, our string action, and instead of being free strings in flat space, if we could, in principle, resum all these terms, it would exponentiate, give some additional term in the action, which we could then try to interpret as saying, now the string background is different. The string is moving, but because of all this insertion of vertex operators, the net effect is that the background was modified. In other words, what we have here in more physical terms is that a condensate of gravitons, which are these closed strings in particular, could very well, we can think of what is a space-time is a condensate of gravitons. We put many gravitons, so many gravitons that they back-react and they change space-time. So again, this is just hinting at what kind of things we should expect. What we should expect is that we can either consider all this sum over all these interactions, and this left-hand side of this picture is the analog of our Feynman diagrams. Or we can trade it for this non-trivial background, where this right-hand side, we should think, will be the analog of the background, and we expect to have closed strings in a non-trivial space-time. Again, we are just building up our intuition. We will soon try to be a little bit more precise. We cannot be much more precise. Okay? So that's, again, starting to approach something more and more close to what will be ADS-CFT. Now, what about this left-hand side? How to be more precise about this left-hand side? What is this left-hand side? It's describing the dynamics of open strings on a brane. Right? So it's open strings on a brane. What are the dynamics of the excitations of the branes? Well, this you saw in your string theory course. These are gauge bosons, and the transverse excitations are scalars. So in fact, the dynamics, the low energy dynamics, the dynamics of this will be the left-hand side, we will see, will give Young-Mills, in particular equals forward spring Mills, plus higher derivatives, which are irrelevant, as we will see. Which are just these gauge bosons that are here, describe the fluctuations of the brane. Indeed, if you think a little bit, what would happen if the string tension is very big? Let's take this picture and think, what happens when the string tension is very big? The string tension being very big is the case when string theory becomes field theory. Because if the string tension is huge, strings shrink, they look like points. So this is the case where strings look like point-like, so this is the field theory limit. What happens if the string tension is huge? If the string tension is huge, you'll see this line here that goes from here and comes back here, these 2 points need to be very close to each other, right? So the separation between the two endpoints of the string need to be very close. So at large string tension, the pictures on the brain if you follow the endpoints, what do you see as pictures on this brain? You see nothing but, if I just draw the endpoints of the string on the brain, I will see that I will have, say, a piece of string like this, which looks like our fat propagators that we had before. And then these strings could interact with each other and exchange some other open string, and the two endpoints of the open string are very close because the string is stretched very close to each other. And then these strings can propagate further, and these open strings can split into two, and so on and so forth. And you see that we start reconstructing exactly the diagrams that we had in our non-abelian gauge theories when we were starting to draw our planar diagrams. You see? So this is how we see this is nothing but the Tooth diagrams emerge. But the Tooth diagrams were not just drawing some fat things. It was drawing the indices, right? So what we were drawing was we put some arrows, and we say this is I and this is J. What is I and J now? I and J now is on which brain is this endpoint. So we have an endpoint on the string that can be attached to this paper. It comes out, and then it comes in, and the other endpoint can be attached on a brain number J instead of brain I, which are at the same position in space-time, but it can be two different brains. So this is the idea of Shan-Patton factors, which is when we have a propagator, if I put an I here, it means that this endpoint is at brain I, and this endpoint is attached to brain J. So to answer the question of someone that asked, why do we need many brains? We need many brains if we want to make contact with these large N gauge theories, where we will have now these diagrams, and where we will recover a large N expansion. Okay? And the other reason is that we want many brains because we want this object to be very heavy to be able to trade it for a background. Okay. So this is the cartoonish intuition, the physics if you want. And now let me tell you a little bit more details.
Pedro.
But one second. Yes.
So I'm just trying to understand this argument of needing like extra brains, because the way you've drawn this diagram, there's no restriction to having to put it on any particular brains at all. So what? How? I mean, because with a T-hoof diagram, like your 1/n factor that contributes the contribution the diagram gives is fixed. Here, I'm just trying to see. Is it a combinatorial thing?
Yeah, we will see.
Right. Okay.
We will see.
Right.
It's the same thing. Okay. So now, let's ask what happens, how to make this picture more precise. So we start with the left-hand side, where we think that we have some probes, and we will study the interaction of our probes with our brains. So we will have our action, which will be the action for the fields on the brane, plus some interaction energy, action, plus some background, some bulk. Action bulk we call the space outside the brane. So this is where we have gravity, which are our closed strings moving around. And this brane here, if we study the action, if we write down the action, and so on, what do we get here? Here we will get, as you know, as you have seen, open strings give gauge bosons. Specifically, if you have superstrings, it gives n equals 1 super Young-Mills in 10 dimensions. So here we get reduction of d equals 10 super Young-Mills to 4 dimensions, which we know is just n equals 4 super Young-Mills. Plus, if we integrate out all higher fields, you start getting higher derivative corrections. In other words, what you get here is really a Born-in-Feld type action, which is just Young-Mills plus some corrections like alpha prime f to the 4 plus dot dot dot, which are higher derivative corrections. Okay? This is just a low energy. So now we are thinking of this as a low energy expansion.
So
yes.
From what you did on Friday, just looking at the 10 kilograms and going 4, how would we see these corrections?
Sorry?
From what
No. This is the n equals 4. This is just n equals 4. We drop all these corrections.
I see. No, but from how you tried to construct it
From 10 dimensions?
Yeah. So like.
Because in 10 dimensions, we don't start with just Young-Mills. We start with Born-in-Feld.
Right.
And Born-in-Feld is more than Young-Mills. Born-in-Feld is Young-Mills plus other terms. And those other terms, when we compactify, give these higher terms. Now, these higher terms, they are dimensionful. This has some dimension. So the dimensionless quantity that you can construct here, if you have some process with some energy k squared, if you scatter some momentum k, so these terms here are of order alpha prime k squared, if k is some momentum of some scattering process, when you scatter 2 excitations. So this becomes very small at low energies when these momenta are small. This is just the usual thing of effective field theory. In effective field theory, you always write some operators, and then you write a bunch of relevant operators, which at low energies become irrelevant. And they don't contribute, just dimensional analysis. In fact, it's the same with all other terms. The interaction part and the bulk, gravity, for example, is weak at low energy, at long distances. So all these terms, in fact, if I take a low energy limit, this is the only thing that survives. So this is the only survival at low energies. Yes. The interaction part is also dimensionful, we can see, so it also drops out if I take low energies.
It's the interaction between the string and the brane?
Exactly. This would be the interaction between its closed strings between gravitons and gluons. This would be the terms that would couple the degrees of freedom here, which are our gluons, and the degrees of freedom here, which are our gravitons. And then there would be some action that would couple both. And the point is that as we take low energy, what happens at low energy is that we get, as we take some low energy limit, I mean, it's at the essence of why we do experiments in the lab. Gravity is irrelevant. We take low energy and we can forget about gravity. And what we get in our lab when we take low energies is that we get, from this description, we get n equals 4 super Young-Mills in 4 dimensions, plus 10-dimensional supergravity. That is, then we have the gravitons that are moving at infinity, free, far away from the brane. They don't even know there is a brane, and they are just moving and doing their life, and then it's just the usual closed string, degrees of freedom, all these gravitons moving around and so on, which is, they are decoupled from the rest of us. Okay? Okay? Good. Now, what about the right-hand side? What about the right-hand side? So now about the right-hand side, we want to ask what is the background generated by these infinite planes, which are these branes. Okay? So how would you do to find what's the background generated by an infinite plane in string theory at low energy? Well, let me tell you, but again, I hope you would accept this, that in string theory, we know that low energy description of string theory is supergravity. Okay? So we can, how do we derive this, by the way? Can someone tell me how do we derive the supergravity action or the supergravity equations of motion from string theory?
Vanishing of the beta functions.
Is this familiar to everyone? No? So the basic idea is that in string theory, when you write that you have some string moving in some general background, so you start and you write your action for your string as some integral, and you write some general metric. Where this is the metric on the worldsheet and that G is the metric in space-time. So this X is a vector in d dimensions of space-time, and A and B take value sigma and tau are the dimensions on the worldsheet. And for this to be a string theory, the basic constraint that this should be a conformal field theory, a two-dimensional conformal field theory. So what you do is you impose that the beta function for this field here, for this metric, is equal to 0. And imposing that the corresponding beta function for this coupling that has two indices, so it's like a beta mu nu, equal to 0, is equivalent to the equations of motion for 10-dimensional supergravity, from which you derive an action that is generated in a way to generate these equations of motion. This is how we understand that string theory, self-consistency of string theory, the fact we try to see can it move in any background as a conformal field theory? No. If we write any background, then try to check for which backgrounds would I generate a conformal field theory that would be a consistent string theory. I found that I cannot put any background. Backgrounds must obey the same equations of motion as supergravity, and this is how we see that the low energy limit of string theory gives as a good limit, and it gives general relativity plus other fields, which is supergravity. So what we can do is go to these equations of motion and put a source and try to find what's the background for a plane. So what we do is we put some source, delta function, when this x transverse equal to 0, right? When we are approaching this plane, it's like how we would find Schwarzschild solution. We put a source at x equal to 0. Now we put a source that is more delocalized. It's a source in an hyperplane, right? This source, clearly, you see, if you put a stack of n branes, this start will be proportional to n, how many units of brane you put there. And you go and you find this solution to this generalized Einstein equations, which approaches this plane as this x transverse is going to 0 and so on. Okay? And in this way, you read off the background. Let me tell you what background you get. The background you get is the following. ds squared, you get eta mu nu dx mu dx nu, where x mu and x nu are the directions here along the brane, x mu and x nu, and the directions orthogonal to the brane, I would call them xi. Like in our scalars, we have a mu and then we have phi I. It's not a coincidence that I'm using these coordinates. And the action you get is just this, divided by square root 1 plus L to the 4 over R to the 4, plus the same square root up here, dxi dxi. So where again, mu, because we are putting the three branes, goes from 0 to 3, and I runs from 1 to 6. Okay? Or I should probably put 4 to 9 because I'm using the same letter x. It might be a bit confusing, but okay. So you know what I'm talking about, right? And this r is just xi. Xi is just the distance from the brane. Of course, this should only depend on the distance from the brane, which is r. Okay?
Could you once again repeat the physical picture, how to get the background?
How to get the background? You solve Einstein equations with a source. The source is the matter that you put. And what you have to do is look for solutions that have this symmetry, namely that They don't depend on where you are on x mu. There is translation invariant in x mu, right? And then they only depend on the distance orthogonal to this plane, right? And then there is a delta function source localized at this plane, which tells you how many branes you have there. And then you would solve this equation, these equations, and you would get this background. Okay? So 1 second. And this would be a good approximation if L, which you can relate this parameter L to this number of branes and so on. Let me tell you what the map goes. L, which L to the 4 is G string times n times 4 pi alpha prime square, is much bigger than 1. So if the length in string units is much bigger than 1, which means that the background is weakly curved, then this gravity approximation will be good. And what we see is that here is the 't Hooft coupling. So this gravity approximation will be good in the opposite regime as to the gauge theory. The gauge theory is good when the weak 't Hooft coupling is small, and this background is good if the 't Hooft coupling is large. That was the question.
So you said we get a background solution by solving Einstein field equations, but we don't have just GR here, we have Sugra. So like,
yeah, so the equations are a bit more.
We have to solve for?
Sorry? Yes, that's right. We have to solve for the metric, for the Dillot, and so on. It's a bit more complicated. I'm oversimplifying. Yeah, we solve the generalization of Einstein equations. When I say Einstein equations, I mean the equations that 10-dimensional supergravity. We solve them. After solving, we look for the metric, and the metric gives that. But there can be other fields excited, and you're right, there will be.
So what are the fundamental fields in supergravity?
The ones that are interesting here is G mu nu, B mu nu, and phi. The fields that you saw in string theory, the same ones. Okay, so now we need to go on a little bit more and try to study a bit the physics of this background. And there are, of course, two interesting regimes to consider. There is the far away from the brain, which means R much bigger than L, or close to the brain, which means R much smaller than L. So when we are very far away from the brain, what happens? These square roots go to 1, and the metric just goes to the matrix of 10-dimensional Minkowski space. Right? dx mu plus dxi dxi. Okay, so big surprise. We are very far away from the brain. We don't see the brain. Right? Just see flat space. Okay? So here, very far away from the brain, we will have our strings moving around. We will have our 10-dimensional supergravity fields flying around far away from the brain. Then we have the region close to the brain. For R much smaller than L. Now, when R is much smaller than L, this term here in the square root, the second term, is much bigger than 1. So it's actually the only term that matters. So it's the opposite. In that case, the metric becomes equal to, I will write it down, R square over L square from the first square root, eta mu nu dx mu dx nu. Now I will write the remaining part in spherical coordinates. So I write L square over R square dr square. I'm writing now dxi dxi in radial coordinates. And I'm putting the bracket here. The radial coordinate, I keep it here, plus L square times the metric how do I write this? Of a 5 sphere. So I'm just writing dxi dxi as dr square plus r square metric of a 5 sphere. Okay? Now this part here, this space-time here, is what is called ADS5 space-time. And this is S5 space-time. It's a sphere. So in total, this space-time becomes what people call AdS5 times S5. It's a particular curved space-time. It's called AdS5 times S5. And a sphere, we know what it is. It's a football ball. And this AdS5, you will see in the exercise, if you did the homework, that it's not very different. Instead of being a sphere, actually you can think of this guy as an hyperboloid. So it's also constant curvature, but negative curvature instead of positive curvature. Okay? So we get some nice space-time here close to the brain. We get the product of an hyperboloid times a sphere. This is the geometry as we zoom in close to the brain. Okay?
So is the statement that going far away will lead to Minkowski a statement of just asymptotic flatness of AdS5 times S5?
Can you repeat?
So I'm a bit confused because you're saying that you have this space-time with the brain, but it looks like you have some situation where there's some kind of asymptotic flatness scenario where you go away from.
Very good. There is. That's right. So now let's continue exploring. We are not done yet. This is where we are on to go. So because now comes the most important part. When I said that that this is a very important argument here in theoretical physics, now I'm reaching to the crux of the argument, which is the statement that the physics here and the physics here decouple. And this is what is called the decoupling argument that I said before. So now let's go and see how this could work. Okay? Now let's see how this could work. So the basic idea is the following. What is the time measured by, what is delta t? Right? T is a coordinate. What is delta t? Delta t is the time. But time, we know in coordinates mean nothing. So we have to be careful. So this is the time measured by someone at infinity. Measured by an observer at infinity. Why? Because at infinity, ds squared becomes dt squared plus dot dot dot. So delta t is time measured by someone at infinity. On the other hand, R over L times delta t, right? This will be the time measured by an observer close to the brain. Right? The time is just ds squared is the proper time, so we just go and see R over L times ds squared. So if we fix the other coordinates to be constant, this is what I get if I am close to the brain. Okay? And given that, and therefore, I conclude that the energies, which are now in the same way, if I flip energies, I just flip these relations. The energies measured by someone at infinity would be related to L over R times the energies by someone close to the brain. Sorry, I'm doing something wrong. Let me think. No, I did the opposite, right? So if I plug this here, then I pass this here, I get L over R, and then when I flip, I get R over L. Right? You see, I compared both times, and then for energies, I flipped the relation. Right? What's true for delta t, the inverse is true for delta E. Is it okay? Please see, this is the most important thing. Is this R over L crucial than L over L? Okay? Do you agree? So it means, this means the following. This means the following. It means that if I start here close to the brain, and here are two friends, right? And this guy has some big plutonium, very energetic plutonium here, close to the brain, some energy. And then if this energy, if this was the energy as measured close to the brain, as he is going away from the brain, as he is going far away, for him, this is becoming a very dim piece of plutonium. This energy, that any energy that I put here, because R is very small, is redshifted enormously, and seen from infinity looks like a very, very low energy excitation. So for this guy, there are two kinds of low energy things. What are these two kinds of low energy stuff that this guy sees? Well, he sees 10-dimensional supergravity, all these gravitons moving around close to him when he's at infinity, plus anything. Right? Anything, if that anything is close to the brain. Anything close to the brain, seen from somewhere very far away, looks like it has a very, very low energy. Whatever you put close to the brain. And of course, what is anything? Anything will be AdS5 times S5 strings. String theory. That's the full thing close to the brain. It doesn't include just low energy degrees of freedom like gravitons, but it includes everything. All massive states, all these pieces of plutonium, all this heavy stuff, everything close to the brain looks like low energy. Okay? And the point is that this sign plus means decoupling. Why? Because AdS5 is a box. If you start taking stuff in the middle of AdS5 and throwing it away, things come back. If you did the exercise, you will see. So AdS5 is a gravitational box. If I take stuff here, I throw it away, it comes back. So there is a decoupling between these two effects. They decouple since AdS is a box. And this is extremely important because now we go and we claim we have one system that is described by n equals 4 super Yang-Mills decoupled plus 10-dimensional supergravity. This is equal to that. But now we just cross out stuff. This we cross out with this. And therefore, we derive, we conclude that n equals 4 super Yang-Mills in 4 dimensions is equal to AdS5 times S5 string theory. Double box. Which is the famous statement of holography or ADS CFT. So this is the sketch of the argument. You could ask me whether I could spend instead of 1 lecture 2 lectures and make it much more precise such that it would be a theorem instead of a sketch. The answer is no. I mean, there are several loopholes. We took some low energy limit and then we are comparing both, cancelling this stuff. Typically, we cancel equations. We don't cancel expressions like this. So it's kind of a bit hand-waving. But physically, it looks okay. So we have the right physically to expect it. It looks reasonable. It's a very good guess. It's a very reasonable conjecture. Then we have two options. One option is trying to develop some formula to making this rigorous and trying to find the sharper argument, clean up the several points, explain this decoupling more carefully, see in which instances it holds or not. Try to clean up all this, when are all these approximations valid or not valid, and so on. That's one direction. The other direction, if we are more pragmatic, perhaps we can do some check. Let's try to see if it works. Let's try to work out a dictionary between the right and left-hand side and compute something so non-trivial that if it works and if both sides give me the same result, I will say, okay, I give up. I trust, probably it's correct. This duality must be true. And I think the second option for sure we have right now. There are some checks that if you would believe that it's a coincidence and that this could work, you would have to believe that you could win the lottery like 5 times in a row. I mean, I think it's more likely to win the lottery a few times in a row than for these checks to agree. So I think there is very, very little doubt that this conjecture is correct. There are arguments, like the ones I tried to sketch, which can, of course, be made much more precise, that hinted at the original duality. This was more or less the original argument by Maldacena in '97, but it still remains as a true conjecture that we are now going to explore further in the remaining lectures. Okay? But the idea now is we forget now about all these branes, everything, and so on. This was a tool that we used to come up with this correspondence. And now we just say, okay, the guess is that we have this theory. We know what this theory is. We already saw it and started even doing some one-loop computations. This n equals 4 super Young-Mills. Now I should introduce you to what are strings in ADS5 times S5. What is the sigma model that gives you strings in ADS5 times S5? And then once we know the left and right hand side, we can start exploring this duality and seeing what it is teaching us about and how we should think about this ADS CFT. So tomorrow we will start with some more philosophical comments concerning this box and why, and further evidence for this kind of duality from arguments. And then we will make contact and we will then ask, so what is this box telling us about this Christmas present that we saw in the beginning? Okay? So this lecture should have been hard because it is not something easy, but this is the nature of the subject. It's hard. That's why it took someone brilliant to come up with this argument. So please do ask any questions or try to think about it carefully and let me know if you want to discuss at some point.
So to get this correspondence, you had to couple it with 10-dimensional supergravity. Is there any other couplings we know of that you can use to go from one to the other? Like, I mean, I don't know if this question is silly.
So the claim is that the low energy dynamics decouple.
Right.
They don't couple to each other. And because of this decoupling is the standard decoupling that tells you can do experiments in the lab and gravity goes to the stars and it's important for star formation, but we can do our experiments in our tables. So this is the usual decoupling. And there the decoupling is more subtle, is this redshift. Is the statement that this background is such that there is a near horizon region, and this near horizon region is special because anything that goes on there, seen from far away, looks like some very, very low energy excitations. That's a very powerful property of this space-time, that there is a region, you can do whatever you want. You can even form black holes inside that region. You can form black holes, put huge strings, stretch strings enormously, throw nuclear bombs, whatever you do there. Seen from very, very, very far away, it will look like something very dim, almost no light at all coming from there. It will look like some low energy physics. So if this is true, then the two descriptions tell you that this low energy approximation is equal to this full string theory. It's a very crazy conjecture. It's telling you that we have a field theory in 4 dimensions, very standard field theory, like quantum mechanics, basically, right? Quantum mechanics in 4 dimensions, just a field theory in 4 dimensions, is equal to a theory of quantum gravity, full-fledged string theory with everything, non-perturbative everything, in 10 dimensions. It's a very, very powerful holographic the dictionary in the sense of something of much lower dimension and simpler being dual to something much richer and of higher dimensionality. If true, it's of course extremely amazing that it could work and powerful.
So the global solution to these equations is ADS5.
Sorry?
So in all of this, just thinking about the supergravity
Yes.
solution. The global solution is ADS5?
No, the global solution is not ADS5 times S5. The global solution of supergravity is this background. Okay. This background is a background that far away is flat space. And close to the brain is ADS5 times S5.
Right.
And the physics at low energy decouple. Everything you can do close to ADS5 times S5 looks from far away like some low energy experiment that you are doing in your universe. Plus the gravitons that are at infinity this is the full low energy physics from infinity. Yeah. But similarly, the same observer that is at infinity and that thinks from this point of view would say that I have my table where I have n equals 4 super Young-Mills and my gravitons moving around here. They are also 2 decoupled. Then he crosses out the gravitons and gets that table equal to ADS5 times S5. It's really tremendous that this thing exists. In fact, Joe Polchinski was giving at some point some lectures, and there are some lecture notes, and the first exercise of the lecture notes is find out 10 arguments why a 4-dimensional gauge theory cannot be equal to a 10-dimensional string theory. And then exercise number 2 is show that those arguments are wrong. Because a priori, you could imagine immediately trying to find contradictions. How could this never be true? Because it sounds really, really crazy. Yes?
So this 10D super here is without source term. Like this.
That's right. That is just really the free. That's right. Yeah. That's just the closed strings moving around, gravitons, gravitinos, everything, all these closed strings moving around and so on at low energy and so on. Far away from the brain. They don't see the brain.
Could you also just make slightly more precise the
I doubt.
Where the boundary is here and how this is like going to the boundary in some sense, something like that.
That's actually a very good question. We have this ADS space-time. Where is the boundary of this ADS space-time, and how do we see that this is the boundary? From this point of view, the boundary, if you truncate the space-time, is when R is going to infinity. So you take this space-time. Now you forget that there is another completion, but you now only take this space-time, and now R goes all the way from 0 to infinity. And R equal infinity would be what you would call the boundary. Okay, of this space-time here.
Of just the ADS5.
If you want just this ADS5, yeah.
And topologically, that looks like?
When R goes to infinity, what happens? This term drops. And now topologically, it becomes some conformal factor times this metric here. So what is this metric? This is the metric of 4-dimensional space-time. So as R goes to infinity, the boundary of this space-time is Minkowski space in 4 dimensions. This is this holographic picture that we have some curved space-time, like our crystal ball. And the boundary of the crystal ball is what people say this is where n equals 4 is, this is where n equals 4 lives. It comes from this intuition that if we study the boundary, the limit of the space-time when R is very big, you drop this out, and you get here the action, the line element, rescaled of course, but the line element of 4-dimensional Minkowski space. But this I will come back to a bit later, tomorrow.
But when R becomes big, that approximation is no longer valid, and we need to look at the...
No, now you need to be careful because of low energies and so on. Yeah? So you first take a low energy limit. So you say you can put everything in this background, and nothing will come out, ever. Right? So you have to see if you are considering energies which are... So you first take a low energy approximation. Now you know I can stick to this space-time. Now in this space-time, I can take any limit I want. And now, yeah.
Sorry, what's happening to the S5 in all of this?
The S5 is also important. It's a 10-dimensional space-time. The point is that S5 does not have a boundary. So we'll see that typically people, when they think in holography, they think that there is some space, some bulk, with some boundary, and the boundary is where the field theory lives. That's true. The boundary of this 10-dimensional space-time is only 4 dimensions, because 5 of the dimensions don't have a boundary. So it's a bit of misleading to say that typically people say that I have a CFT in d dimensions and ADS in d plus 1. That's typically not totally correct. It's typically you have a CFT in d dimensions, and you have ADS in d plus 1 times some other internal manifolds, such that in total you get 10 dimensionals here, which are the dimensions of string theory. But given that it's an internal manifold, you typically don't, it's not as important as an uncompact part. For example, you could Kaluza-Klein compactify on it and just decompose along modes on this manifold.
Sorry, so that was what was confusing me initially. So the boundary of ADS there is what you call it. The place is called infinity. So it's the same thing. So can you reach through this?
The boundary of ADS 5 times S5 is 4-dimensional Minkowski space.
So, okay, and that's what you're calling...
4-dimensional Minkowski space, not 10-dimensional Minkowski space.
Right.
4-dimensional Minkowski space.
Okay, and
right?
That's what when you're talking about the guy moving there, it's just where it's going.
Sorry, could you repeat? That's
where the other guy is going there, those two in that cartoon.
No, in that original cartoon, this is really in the full picture. In the full picture, the observer is really going to the true infinity of the original background, not to the low energy. Because what I want to argue is that that observer that really goes to the genuine infinity, very, very far away from the brains, he will say that at the brains, whatever you put there, if you approach the brains, it has 0 energy. So if I take this limit careful, I know that things close to the brain decouple from the rest.
Okay.
So this is an argument that is needed to be able to argue that everything seen. Basically, we want to say we have the same observer, which is far away. So we have n equals 4 super young Mills, which is living on that blackboard. And I'm going here. And now I'm studying it from 2 points of view. The background point of view, I say that everything there is low energy. The brain point of view, I say that's my experimental table, and here I have gravitons, and there I have open strings, which is n equals 4 super young Mills. So me, here, far away from the brains, the observer at infinity, has two alternative descriptions. Either I think like that, and I think that I have my open strings interacting there, or I think like this, and I think that I have my closed strings popping out of that background and generating an untrivial background.
So all of this is in that limit, as in this.
I use this observer to claim what is the description. Then I forget about the observer and I derive the duality. It's like, again, the experiment. The Duncan experiment. Cool, okay, so let's continue tomorrow.